Hello students. This is the last lecture on security issues at the storage, right? In this lecture we are going to look at one specific ransomware defense, which is titled SSD-insider plus plus, and I'm also going to give pointers on few other potential issues, uh, security issues at the storage. Right? SSD-insider plus plus was proposed by Seoing Baek in IEEE transactions on computers, and it came out just in 2021 October. So the prior version of this paper was has come out in 2018 itself, which is called SSD-insider. So in general, if we look at the ransomware detection techniques, they can be classified into two groups. One is signature based detection, the other is content based detection. So in signature based detection, we analyze the application's code before we execute it. Means this would come under static analysis. And what typically is done is a particular code string from the application is, which is also termed as signature, is checked with an existing list or repository of such signatures to identify whether the signature will match is matching with any of the ransomwares, known ransomwares, that is, right? So obviously the main limiting factor is because the ransomware implementations have been changing very drastically, the maintaining the repo becomes the key, and updating the repo, the onus will be on that. When it comes to the content based detection, to um, the ransomware's behavior is observed when it is executing, so it's dynamic in nature. And what is typically observed is whether there is a change in the file type, or uh, if there is very low similarity between the original and modified versions of the files, and uh, if there is a change, huge change in the entropy of the files, right? So these would be some of the uh, deciding factors to see whether it would be a ransomware or not. And obviously there are a few set of limitations. One is that such an analysis would require high computation power, also memory usage, right? Also such analysis might typically need some changes in the OS for allowing this uh, software to be run, right? And also because the ransomware is currently executing, some or most of the files of the users are already exposed. So in case the detection takes long time, then the files might be even lost. So that would be the case for detection. Now let's say if we detect that it's a ransomware attack, how can we recover the data? So they are typically classified into three. One is decryption based recovery, second is backup based recovery, third is SSD assisted recovery. As the name says, decryption based recovery tries to use a key or a set of well known keys to decrypt the data, and there is a high chance that it might not work. Coming to the backup based recovery, here a specialized software would try to uh, restore the restore the data from the backup that it takes frequently. So or it can take a backup for every change that happens to the data, or periodically saying that for a week, for every week you take the backup once, or every day. So it depends on the uh, setting itself, right? But a specialized software would be required. Now when we come to the SSD assisted recovery, it is all part of the standard SSD itself, or uh, at least that's what we would expect, that such recovery mechanisms would come in any standard SSD. The very first proposal in this line was FlashGuard, which has come in 2017. Following that, we have the SSD-insider, which has both detection and backup within the SSD. We also have an specialized accelerator in the SSD that would help us in detection and backing up of data, which is called Amoeba. And the one other possible exploration that was done is a delay in the deletion of the data until we are confident that there is ransomware or not. Coming to the SSD-insider plus, it is an SSD-assisted detection and recovery. Right? On the detection front, SSD-insider looks at the header of the IO packet, and it would try to detect patterns of accesses that are unique to the ransomware. Also, looking at the header of this IO packet can help us to make note of all the changes to the files that are happening. If some file has changed, we would know which file it is, where was its original version placed, and where is its newer version placed. Right? This would help us in recovery part. So, because the write in a flash based device does not happen in place, meaning that some new place would be chosen to write the updated value, that feature can potentially help us in recovery. But there are a few design challenges, like how do we keep track of all the old versions of the data, right? And their potential problem can be with maintaining the data consistency after the recovery. The third aspect is that such a recovery process should be lightweight in the sense that the computation that is required should be less. Also, once the recovery starts, it should happen as quickly as possible. Right? Let's look at the detection part of SSD-insider plus. How do we identify a ransomware? Right? Potentially by looking at the access patterns. In that regard, the SSD-insider plus authors have classified different ransomwares into three classes. Class A is the simplest one, where if you observe here, a particular file A is read from the SSD, it is encrypted and overwritten. So here the access pattern would be read and overwrite. Right? Encryption is anyways done on the CPU front. But there are few other ransomwares which are not so easily identified. So here is another class B, which has three different phases. In phase 1, it reads a particular file A and it deletes that particular file. Right? It will write that file into another location. In phase 2, it would read that file from the new location, encrypt that, and overwrite it. So this phase 2 is very similar to class A. Now in phase 3, what it does is it would read the modified file from this new location, delete that file in the newer location, and write it back to the previous location. Now if we want to analyze this particular ransomware, it has a interleaving pattern of reads, writes, and deletions. Right? In the same way, there can be another a class which is class C here, where we are reading a particular file A. We are then deleting it, means we are sending a TRIM command to the SSD. Following that, the ransomware will encrypt this file, create a new file B here, and write it in a newer location. So here, the earlier file and the newer file are totally different in different locations. Right? So class A is where we are writing the encrypted file potentially to the same file. Of course, physically they are different. So this is the in place write, class A, but class B and class C would be out of place writes. Right? So class A is easier to notice, as we observed, but class B and C are a little more difficult. Also, they delete the original files. So recovery in class B and C is more challenging. Right? In addition, these ransomwares don't run alone. they will be potentially be running along with some normal user applications. Now, identifying these patterns at the SSD with an interleaved accesses from the regular applications and ransomware is a more difficult job, right? So to address this issue, the authors have done some analysis. For that analysis, they have used a set of normal applications and a set of ransomwares. For normal applications, they have considered 4 categories. The first one is heavy data erasure based applications, so like data wiping, MySQL, Windows Update, compilation, data copy, etc. Right? And the second category is IO intensive applications. Right? It typically runs a tool IO stress or IO meter. The third one is CPU intensive application, which they have considered as a compression application, and the fourth one is a normal application where a peer-to-peer download application is running like BitTorrent. Right? On the ransomware front, they have considered 5 different ransomwares: WannaCry, JAF, Mole, CryptoShield, Locky, and Zerber. Right? So there are 6 different ransomwares. Sorry. Now, the typical update after read or trim after read together is termed as erasure here, right? Now, the different metrics or the features the authors have proposed to identify the ransomwares, there are 6 such features. We are going to study each one of them, right? The first one is erasure IO. How many times the update after read or trim after read have happened, right? So this would indicate that the file has been read, encrypted, and erased potentially. It's not always, right? So here is the observation of the authors. The graph shows on x-axis the timeline and y-axis the cumulative value of erasure IO, right? The units is 1000. So it means 100 means 100,000 erasure IOs have been observed, right? Now, as the with an increase in the time, you can see that the couple of ransomwares have exhibited high EIO numbers. So specifically the WannaCry and Mole. So these two, right? So these two ransomware applications can easily be identified just by looking at this particular metric, right? But here these ransomwares and applications are run alone, right? The compression is running alone, cloud storage is running alone, etc. But here this is the simplest feature that we can look at, but we cannot identify the JAF or CryptoShield ransomwares here because their behavior is very similar to other normal applications. So to further classify, they have proposed another feature, which is fraction of erasure IO operations over the overall write operations. So the observation the authors make is for applications like data wipe, IO stress, etc. There are multiple writes before any erase operation. So this particular fraction would be very, very low for such normal applications, right? So accordingly, they made few observations. Here again on x-axis we have the timeline, on y-axis we have the fraction of erasure IO over the writes, right? So if we look at this particular graph, we can clearly identify the WannaCry, right, JAF, not JAF, Mole, and the CryptoShield, right? These three have very high FEIO metric or feature, but still we are not able to distinguish the JAF application from the normal applications, right? For that, they have proposed another feature, which is accumulated number of erasure IO operations. Now, the prior two features were being calculated for a very short time slice, they call, which was considered to be 1 second. But there is another time window which is larger, meaning it can be 10 to 15 seconds. So this third metric is calculated over a time window, right? So this will help us to detect those implementations of ransomware which don't issue the erase operations quickly. They deliberately delay it. Okay. Or it can also help us to identify ransomwares which are run along with the normal applications, because the SSD will see an interleaved accesses. So the erase operations of these ransomwares can be potentially moved or delayed at the SSD itself, right? So here again they have considered a mix of ransomware along with the normal application. JAF is run alone, Locky is run along with the Windows update, Zerber is run along with the IO stress, WannaCry is run along with the compression, and cloud storage and peer-to-peer download applications are run alone. So with this, we can see that the Locky and window update, that particular run is exhibiting high number of accumulated eraser IO operations, right? Again, another one which is exhibiting high is the JAF. So finally we are able to detect JAF here. And there are some potential applications which have a similar behavior, like WannaCry and compression has same behavior like the Zerber IO stress, right? So they are very close to the normal applications, but still they are higher. But again, identifying within these can be little tricky, because we still have to wait for 40-50 seconds to make a decision, right? So to further refine their classification, they have proposed another feature, which is average length of continuous erased IO operations, right? Their primary observation was that the ransomware will have short continuous erases, but normal applications will have longer. So in the all the prior graphs, the higher the particular line is, the more the probability that it is a ransomware. But in this graph, the lower the line is, the trend is, the higher the possibility that it's a ransomware. So if we look at the AVIO feature for WannaCry, it is very low. Also JAF, it is very low. But for the other three regular applications, normal applications, it is quite high, right? So they have specifically mentioned that DataWipe and MySQL have large numbers for this particular feature. In addition, they have also proposed two other features which are short slope and long slope. Again, this is motivated by the common observation that there will be an abrupt change in the number of erasures that will be experienced at the SSD when a ransomware is run. So short slope will try to calculate or make a note of these changes in the erasures in a short window of, let's say, 1 second, and long slope will try to identify the changes in the erasures for the longer time window, like 10 seconds or 15 seconds. So with these 6 features, the authors propose to detect a ransomware. That their overall approach is to observe the IO trace, keep calculating these 6 features, give these calculated features to a trained machine learning algorithm. So instead of going for a complex algorithm like an SVM or LSTM, they have proposed to use a simple decision tree, again to reduce the computation power, also speed, right? And their trained decision tree has these look something like this. So they have used the individual metrics to decide whether further classification is needed or not, right? So these numbers are from their trained model. So you can currently say that they are empirical in nature. The very first metric they have used is the accumulated erasure IO operations. If it is less, then most likely that it's a normal application. But if it is more, but less than 3000, then they are going to look at one other metric. If it is less than 15,000, then they are going to look at two other metrics together, even if it is greater than 15,000, they can potentially look at three other metrics to take a decision that it would be it can be a ransomware or not, right? So with that detection mechanism, if let's go to the recovery aspect of the SSD Insider plus plus, right? So here we have the timeline. Okay, so the written LBA is the logical block address and the trim is the erasure, right? So the way we would read it is that there was a first write command for page 0, then page 1, page 2, page 3, then again there is a write for page 0, another write for page 1, there is a write for 4, 5, followed by write for 2, and there was a delete of page 3. Now the mapping table, which is part of the FTL, would start off with entries like 0 would be having the PPA is the physical page address. So 0, because that is the first write that we have seen. Then 1 would be having 1, 2 would be having 2. Following that, 3 would be having 3. Then we have another write for 0. So because we need to write it in out of place, the SSD controller has picked another new block, and the new page, physical page, has been updated here to be 4. Same for the logical block address 1, it has been written in the physical page 5. Following that, we have 2 writes for 4 and 5 here. So those are placed in the physical pages 6 and 7. Then we have a request for write of 2. So the free page in the next block, which is 2, has been chosen, and the free page in the block 2, which is 8, has been chosen, and that entry is updated here. And after that, there is an erase command for 3. So it would be, that particular entry would be made invalid. So this is the normal operation of a typical SSD. Now for SSD-insider plus plus, what the authors have done is they have introduced a new data structure or new structure, which is recovery queue, right? So what it primarily does is it will note down all the changes in the logical block addresses, right? So because there was a write for 0, along with finding the new location to be written and updated in the mapping table, its earlier location is updated here. So earlier the PPA was 0, so that's what was updated here. Same with 1, 2, and 3. So why did 3 happen here? Because it has received a erasure. So if we specifically look at 3, there is no valid entry in the mapping table, but in the recovery queue we still have the location of its data. So let's consider a scenario where at time t, the ransomware has been detected. Now what the SSD-insider plus plus would do is that this mapping table would be updated with the entries of this recovery queue, meaning that this 4 will be replaced by 0, 5 will be replaced by 1, 8 will be replaced by 2, and this particular entry which has been marked invalid will be made valid, and 3 will be written in it. Right? Now this begs a question that how long would this recovery queue be? Right, so this is again a design choice, and the authors propose that the recovery queue will be maintained in the DRAM cache. So we can potentially have a few hundreds of entries in the recovery queue, and their experiments have said that shown that these few hundred entries are sufficient most of the time. So once a ransomware attack has been detected, right, what the SSD-insider does is that it makes the SSD to stall all the writes, and the device would become read-only. Means all the write requests would either be squashed or stalled at the SSD, right? It would send an explicit ransomware attack alarm to the host device. So this needs a small change in the standard SSD host interface, And along with the alarm, the SSD-insider sends a request to give the rollback time to the user. It means that uh, the user is expected to choose the time to which the data has to be restored to, meaning that the data, 1 day's old data is what is needed, or 1 hour or 1 week, etc. Right? So based on that time, the recovery would take place. Using this time and using it along with the recovery queue and mapping table, all the modified pages will be remapped to their old pages or the valid pages, right? But there can be a potential data consistency issue. For that, the user would require to run fsck command. That would be typically done even if there is an abrupt power loss also. So the authors have shown that this is sufficient. And to support such a recovery operation, there are few changes that are needed in the garbage collector, right? A copy of all the pages in an old block are needed, right? So earlier the garbage collector would simply discard those pages for which the entries are marked as invalid. But now what we need to do is even all those pages would be required to be moved to the new block. Now that begs a question: why would we require to move a new to a block, right? But these invalid pages are those which are falling in that particular time window only. Means that we would wait for a specific time specified as T back by the authors, which can be typically 2 to 4 weeks. Means all those pages which are marked as invalid over the past 2 to 4 weeks will still need to be maintained. But beyond that, they can be discarded, right? That small change is needed in the garbage collector. So with all these in place, the detection and recovery in place, there can be a potential case where the SSD-insider has failed to detect the ransomware with the features that are there. They were not able to distinguish. What happens in that case, right? So the authors have proposed a lazy detection implementation, wherein the observation is that the entropy of the pages that were encrypted by ransomware is usually high. So they have given an example where they have considered 8 different files, right? And some of them have very low entropy and some of them have very high entropy, right? After the files were infected with ransomware, almost all the files have high entropy. So there are very few, earlier at least some of the files were having low entropy. So this abrupt change in entropy can potentially be the result of an ransomware attack, right? So this entropy based detection can be used to do some recovery, but there is a limitation here that the pages that have been deleted using the trim command might not will not have an entropy, because only one entry will be there. Their old values original file will be there, even if it was not deleted by the garbage collector, but it cannot be compared with, right? The other challenge is that such entropy calculation requires a lot of computation that needs to be done, and SSD being a very small device with a very specific power area and performance parametrics, supporting such entropy calculation can be challenged. So it can be deployed occasionally whenever a backup is being taken. Just before the backup, if you want to know whether there was a ransomware attack or not, the entropy of the pages can be looked at. Or every once in a while, for few random pages, these entropy calculation can be done, and if there is a change, then we can potentially take the corrective measures. Or there can be a a dedicated accelerator for such entropy calculation and detection of possible ransomware. So these were the three approaches the authors have hinted at. And whatever the method is, such entropy difference or changes in the entropy are observed across a large number of pages, and if for majority of these pages the entropy change is high, then it can hint at the ransomware attack. So with that, I will conclude the discussion of this paper. This paper titled SSD-assisted Ransomware Detection and Recovery Data Recovery Techniques is your first reading assignment. You need to submit a 2 to 3 page summary of this particular paper, and a lot of design space exploration was done by the authors. Do go through the experimental analysis also, and you would be expected to write all the possible limitations of such an approach, right, and strengths of an approach of this approach, etc., in your summary. Along with that, if the whole ransomware concept intrigues you, you can look at the existing literature: FlashGuard, Amoeba, Ransom Blocker, or Freedom. Or if you are interested in ML based ransomware detection, then there is an open source dataset that was released just a few weeks back, and it's published in Elsevier, which is called Ransap. Have a look at this paper. You can get the traces with which you can work and explore new different ML algorithms and see how well they perform. What other possible improvements can be done for detection and recovery for ransomware is potentially we were looking at early detection, but we stopped at SSD. Can we do something at caches or main memory? The main limitation is the size of these structures itself. The caches are few hundreds of megabytes at most, and the main memory is few gigabytes, right? So we need to come up with some efficient way of identifying these patterns given such a space limitation, right? Because there will be only few thousands of blocks in the caches and probably few thousands of pages in the DRAM that we need to observe. But there can be some other pattern, like there might be increased page faults, etc., that can be potentially be looked at. And there are no prior techniques of using the disk cache for detection of this ransomware. That can be a potential area. Following that, there is no specialized RAID level which is designed to handle these ransomware attacks, right? As you are aware, there are various levels of RAID, 0 to 6 or 7, and there is a combination of RAID levels also. So a potential exploration can be done on how they fare against these ransomwares, right? Can they help us, or they are equally vulnerable, right? So that is a very good study. And in general, many of the applications can potentially have this read-write behavior, right? Now, when we run ransomware along with such applications, the features that the authors have proposed might not even work. So maybe a better set of metrics or features are needed, but that would require you to run the normal applications along with the ransomware and see where these metrics are failing, right? Better classification, that's what I wanted to take away from that. So the threat model that we have seen at the storage so far is where malware has is trying to encrypt your data files, and how you can potentially save yourself that save the user data, right? But there are other threat models also, and the popular one is the adversary has the physical possession of your drive, like he has stolen it, or uh, or he has some other device which can take a copy of all your device, all your data, etc. Right? So if the physical position is an threat model, then one of the best defense is to encrypt the entire drive or encrypt a few set of files that the user feels important. But the major challenge with encryption is that it's very compute intensive and power consuming, right? So power hungry, as they say. So there can be potential optimizations that can be looked at. Other way of limiting the access of the adversary is to employ access control memory, meaning the generic example is whenever you're trying to enter a building, there is a security guard there. So here, uh, in the same way, you would need to give a password to access some particular memory location, or you would need to scan your fingerprint to access the contents of the SSD. So Samsung T7 SSD has come up with a fingerprint sensor also. It is basically an access control based memory design, right? But again, that's not fail proof, so there are some potential issues there. The other one is where the adversary is trying to recover some of the files that you have deleted. Now, why can this be a headache to us? As you know, we cannot the garbage collector will kick in a little later. It's not that your file is immediately deleted. Also, during the entire usage of the file, you can write to it probably multiple times, and that each version of the file can be stored in different physical location. Now, eventually, when you try to delete the file, right, all these physical locations need to be individually deleted. If those locations are left just like that, then the adversary can recover the critical data from that. Another threat model is where the adversary has given us a infected USB, and that can potentially sabotage your entire system, right? So again, how to design a secure USB is one of the research areas, right? I have given some indicative works, so interested uh, guys among you can go through them, right? So with that, I will